Hey everyone. So at the end of my 30-minute video, the part 2 of 2 for this lecture, this section, I realized I forgot to mention a pretty important theorem slash consequence of permutation expansion. So like the main thing that I wanted you to get away from this section is how do you compute permutation expansions? What are permutation expansions? What are they useful for? But one other thing that they are useful for is the following theorem. So the determinant of a matrix and the determinant of its transpose are exactly the same. This is not obvious based off of our definition. Effectively, this comes from the fact that if you look at the permutation expansion of a matrix and its transpose, they just turn out to be the same. You could kind of just like look at a different permutation and because of the permutation expansion formula that you can write down, which I'm not bothering to write down the formula because it's not particularly useful to know the formula. But based off of that, you can make this conclusion. I'm not going to go through this proof or anything. I just really want you to know this because it's a pretty widely used fact, and it's very commonly seen. A corollary to that is that you can talk about columns with matrices. So what I mean by that, so if you have a matrix with two equal columns, that would be singular. That tells you, if the determinant would be 0 if you have two equal columns, and that's because we already know that the determinant of a matrix is equal to 0 if we have two equal rows. So like all of the theorems that we said in the previous section about like, oh, a matrix is singular if blah happens, where blah is like some property of rows, you can just replace rows with columns, and that all that stuff follows through just because you can just transpose your matrix and make rows into columns and columns into rows. So yeah, that's one fact. Column swaps change the sign of a determinant. Same thing with row swaps. And determinants are multilinear in their columns. So all of this is basically just coming from, maybe I can scroll up to the definition of permutation expansions. Yeah, so here our definition of multilinear says, so we were thinking of V as being consisting of rows of our matrices, and V to the n was our matrix that way. You could just think of V as being a column and V to the n as being your matrix consisting of n columns that way. And now instead of rho sub I, maybe you would put like a C sub I to represent a column, and you could just do all of this stuff this way. So all of these things could represent columns, and this is in particular one of the main reasons why the determinant of a matrix and the determinant of its transpose are the same. This is pretty important for that. So anyway, well, I wouldn't say that it's the reason why that happens. It really comes from the permutation expansion, but anyway, hopefully what I'm saying is making sense here. Permutation expansions are also useful for deriving Laplace's formula, which is also known as cofactor expansion. We're going to talk about that in a later section. So anyway, there's the addendum to that video. That should be everything.